A classic example of an application of differential equations is Newton's law of heating and cooling. This law is written down here. The rate of change of temperature of an object, so H is the temperature of some object in the environment, is proportional to, or is a constant times, the difference between the temperature of the object and that of its environment, or literally the difference, the subtraction of H minus T environment. The parameter that is put in here as the constant of proportionality, we call it here alpha, is going to be something that involves the heat capacity, the surface area, things like that related to the object. The idea, though, is that given a certain object, this would be constant, and so we would have a rate of change of the temperature dictated by the difference between the temperature of the object and the environment, and modified by that rate constant there. One of the important things when analyzing differential equations is looking at the signs, because we know sign has a huge impact when we come to interpreting derivative values, positive meaning increasing and negative meaning decreasing. We explicitly put this negative sign out front because we like to have our constants positive in these to make the signs really evident. In this case here, alpha must be positive if we're going to have our usual understanding of how heating and cooling works. For example, if H is bigger than the environment temperature, what does that mean? It means our object is hotter than the environment. If that's the case, well, we can translate that to H minus the environment temperature will be positive. Bring that back to our differential equation, we would have a positive value here, a negative value here, and what do we know about the rate of change of the temperature? Well, if you have something hotter than the environment, take a hot coffee out, put it outside in the snow, the object is going to be cooling, and if the object cools, then that means the derivative with respect to time must be negative. Well, if this is negative on this side, this is positive, there's a minus sign out front. The only way to have that work is to have our alpha be a positive quantity. Now, a reasonable suspicion at this point would be that, well, what about the other direction? What about when things are heating up? Well, if we have H less than the environment temperature, in other words, our object is colder than our environment, what kind of consequences can we expect there? Well, the H is going to be H minus T environment in that scenario. H minus T environment is going to be negative. Let's say our environment's at 100 degrees and we're at 0, then 0 minus 100 will end up being negative. So let's take a quick sign check here. We'll erase all the signs we had before. Now we have a negative value for this difference. We have a negative out front, and we know now, under that scenario, that our object is too cold, it's in a warm environment, our object is going to heat up, and that means our derivative dH dt must be positive. So we must have a positive thing here. How's that going to work? Only if alpha is positive. And so what we see is what we call sometimes the magic of the thermos. The thermos knows, in some sense, that if you put hot objects in it, it'll keep them hot, and if you put cold objects in it, it'll keep you cold. The physics interpretation is that the constant that shows up in these equations is the same regardless of what's happening in the situation. This constant is the same, and the signs work themselves out in relation between the temperature difference and the rate at which the temperature is going to be changing, whether it's positive or a negative rate. So this way of writing out the Newton's law of heating and cooling is quite nice because it lets us do a quick analysis and explicitly has the signs available to us. If I want to know whether this rate is negative or positive, I can almost see it at a glance, knowing something about my temperature and the environmental temperatures. All right, with that being said, let's take a look at an example. Let's imagine we take a potato at room temperature and we put it in an oven at 200 degrees Celsius. And that interpretation for our mathematics is that T environmental will be 200 degrees. We're going to assume a value for the constant alpha, and we're going to measure things in minutes. What does this lead us to? Well, we've pretty much filled in all the blanks for our differential equation here. Let's put it in the abstract form here. And then we'll fill in the blanks with the values we now know. All right. It's important to note that I only filled in the 200 and the 0.25. The H equals 20. The important thing with that is that that's the initial temperature only. It's not true in general. In fact, we know, if I asked you, hey, I take this potato out of the fridge or off the counter and put it in this oven at 200 degrees, is it going to stay at 20 degrees? Well, hopefully not. The point of putting it in the oven is that it's going to cook. So all we know about the temperature of the potato is that it started at 20 degrees, but it most likely is going to increase from there. So all we know is the initial temperature, but not the overall temperature in the future. In fact, that's what our goal is going to be, or our question. What is H as a function of time? And this goes back to the kinds of questions we can ask. How long will it take for this potato to be done? If we know what temperature would have the potato cooked, then we can talk about how long that'll take once we have solved this differential equation. All right, so our equation, dH dt, is minus 0.25 H minus 200. And now we can go ahead and solve this differential equation with the goal of finding H equals. Okay. The only technique we have at our disposal at the moment is separation of variables, so we'll do that right now. We're going to separate our sides, and I'll bring the H minus 200 down. I'll leave the negative 0.25 up on the right side. It's not in the way, we'll keep it there. And then we're going to integrate as well. Okay, so we put an integral sign, and away we go. The right-hand side is nice and straightforward. It will be negative 0.25 t's. And on the left-hand side, you have to be a bit careful, but it's a ln of H minus 200 in absolute values. And we have a dH here, so the H's match, we're good there. And last but not least, we need a plus C. We include it on the right-hand side because we're going to try to solve for H. That means putting most things on the right-hand side. Okay, so we've separated our variables, we've integrated, and now we just have a regular equation involving H. So now we can solve for H. All right. What do we need to do next? Well, we need to get rid of this ln. I want H. We need to get rid of the ln. So we're going to exponentiate both sides, or use e as a base for both sides. The exponential of ln undoes each other. On the other side, we get e to the negative 0.25 t. And because it's e all to the power of this, we can also treat it as e to the power c multiplying the other exponential. And here's where we do one of our tricks. We would like to get rid of this e to the c. We'd also like to get rid of these absolute values. So what we usually would do is define a new variable as e to the c here. And what we're going to do as well is make that positive, make our a value positive or negative, whatever would make these absolute values work out. Let's see how that plays out here. So if we take away these absolute values, that might change the sign of the right-hand side. And so what we're going to do is just lump that sign into something called A. So that's the only thing that changes on the right. On the left, we can get rid of our absolute values. All right. Last but not least, we can solve for H. We're almost there. H, in fact, is equal to 200 plus A e to the minus 0.25 t. And that would be our general solution. Fantastic, actually. So, are we done? Well, wait a minute, hold on. We wanted a solution for this particular potato, and for that, we also have some initial conditions. the initial condition of being 20 degrees at the start time. So if we sub that in, that means that h is 20 when t is 0. So we'll plug that in, 20 equals 200 plus a e to the 0. Put that in color too, there we go. And that means that negative 180 is equal to a. So h of t, the temperature of the potato, is going to equal 200 minus 180 e to the negative 0.25 t. And that is the specific solution that applies to this scenario here. Starting at 20 degrees, we use that piece of information, but being in a 200-degree oven. All right. Last but not least, let's try to answer a question that we couldn't have answered with only the differential equation. Questions of how long are something we need the solution for. Let's take a look at that on the next page. So when does, or what is the temperature rather, at time equals 10? Well, that is as easy as plugging in 10 into our temperature function. It'll be 200 minus 180 e to the negative 0.25, and this 10 is our time value. And if we plug that in, we can do a quick calculation, and we're going to get 200 minus 180 times a number that's around 0.08208. That's an approximation already, and if we simplify that a bit, we'll be at 185.2 degrees Celsius. Okay, so what does that mean in terms of our modeling? Well, what we just said is, if we had a graph of temperature versus time, if we started at 20, we know we're in a 200-degree environment. Well, after 10 minutes, we would have heated up, and we would have gotten almost up to 185. So this is a very small potato. Most potatoes don't heat up that quickly. But after 10 minutes, we're already at 185 degrees Celsius and well on our way towards the 200-degree environment that it's living in. What we found in that analysis was a particular solution to the differential equation, and what it meant was, or the interpretation was, we could predict what the temperature of the potato would be over time. Now that's interesting, but sometimes we'd like to generalize that idea, and we can do that by looking at slope fields and using some of the other techniques from the previous unit. Let's take a look at some of the values here. Here's our differential equation, and notice all it depends on is h, which is the vertical axis on our diagram here. All right, with that, what we could do is estimate some of the slopes. In fact, that's all we need is two values here. Let's say h is 0, 100, 200, and 300. That's the temperature. Then the slope at each of those values of temperature would be, at 0, it'll be 0.25, 0 minus 200, we'll have plus 200 times 0.25, or a quarter of that, which is 50. If it's 100, we'd have 100 minus 200, and that'll be positive or negative 100 times 0.25 is 25. Interesting case here, if h is 200, 200 minus 200 is actually 0, and then we would have, if you get your calculator out, negative 25. What does that mean in terms of a diagram like a slope field here? Well, at temperature 0, we have a slope of 50. And it doesn't matter what time it is, as long as I'm at temperature 0 degrees Celsius, then the slope will be 50. So that would get us up slope like that, pointing at that point there. And it'll be the same all the way along regardless of the time, because the slope only depends on h. Contrast that with the 25 slope, which would be like this. Rise of 50, run of 2, that's slope of 25. And then contrast it even more with the 0 slope at 200. And last but not least, the slope of negative 25 at 300. Okay. So how do we interpret this? Well, we started for this particular example around temperature 20, and what we see is something pretty steep. Then when we hit here, we hit slope that looks like that. And then we know that the slopes are going to get smaller and smaller, and so we're going to see some kind of exponential decay like that. In fact, after 10 minutes, we're supposed to be at 186. That's a pretty good sketch. This actually matches quite nicely with the analysis we just did. Now, what if we started at a higher temperature? If we'd started at 100 degrees, if our potato had come out of some other oven, of course we'd get up to that temperature faster, but we wouldn't ever exceed 200 degrees. And again, there's a mathematical and a physical reason for that. The physical reason is if we're in an environment of 200, there's no reason for the temperature to ever go above that if we start below. And the math says as we approach 200, the rate of change is going to approach zero. Well, that means a flatter and flatter graph as we get closer and closer to 200 degrees. Now, let's take a look at one of the examples. If the temperature started above that equilibrium, which we'll talk about in a second, if we started above 200 degrees, so imagine taking something out of a hotter oven and putting it into this cooler oven, well, the temperature would decrease. We'd have cooling happening instead of heating. All of that is dictated by this equation. No fuss, no muss, takes care of itself. All of these scenarios are covered by exactly the same equation, and all of these solutions describe realistic scenarios that we could imagine. Given a certain starting temperature, putting it in this oven, what would the temperatures do over time? Well, they'd all converge down or up to 200 degrees Celsius, which is the environmental temperature in the oven.